correlation, it gives me standard. This is a standardized version. Standardized means it also, so standardized means I can now compare these two different data sets. Okay, this is a standardized version of covariance. Earlier I just had the direction. They are positive, I can just say that. But the magnitude, because these are in different units, so these units didn't make me. So age and height would be years and say centimeters. Here again it will be years and say salaries in rupees. So these units are not comparable. So we need to standardize it so that I get rid of the units, and then only they will become comparable. Okay, so the magnitude what I get, if this salary, because salaries will be, height would be like, say the age is in, like age will be, say this is comparable. Height, what would be the range? Say for example 150 to 200 or 250 centimeter, that is the height. But the salary would be something like, say example from some 2 lakh to 1 crore. Say for example this is the, so they are not comparable. So these units, I cannot compare the magnitude and say they are more correlated, these are more correlated. For this new metric was required. That's why we have correlation also. This is a standardized version. How it is standardized, let me tell you. And as I mentioned, it measures both direction plus magnitude of linear relationship. Linear always means straight line. Linear relationship, degree 1. So this gives me, this standardization means this makes it dimensionless. How does it do it? Let's see. So here we have units as years and centimeters. This covariance is in years and centimeters because x and y are in years and centimeters. Here years and rupees. So definitely I cannot compare. So standardizing means I have to get rid of the units. And how do I do it? Many places you will see again and again in machine learning, we standardize the data. Means we'll get rid of the units so that I can compare two kinds of different data sets that I have and see how strongly they are correlated to whatever, in whatever terms we are comparing. Okay, I hope that makes sense. Let's understand how do we do. So there are two ways. So there are two common ways we are doing this. So first one is Pearson. So the range, again I'll tell you just, so the range of values that correlation takes is, so the range of values of correlation is, it goes from +1 to -1. -1 is like, again, so this is the range of values. Here you saw you got 2 also, but correlation after standardization will follow only in this range. -1 is totally negatively correlated, means if x increases, so this is +1, in middle 0, and the complete range, it has the complete range of values. +1 means strong correlation, strong positive correlation, means x increases strongly, y also increases. This is strong negative correlation, if x increases and then y decreases, and this is 0 correlation, no correlation, sorry, ulta, I'll just change here. This is -1 and this is 0. 0 means no correlation, means if x changes whatever, then y no change, nothing is happening. And the ways to measure it is measure correlation, that there are two most common ways to measure this, and the first one is Pearson correlation coefficient. This is denoted generally by symbol R. Okay, and this again, this has a range. I'll write it the same, it has the same range, less than equal to 1. Okay, this is the most widely used Pearson. I'll talk about Spearman's rank correlation coefficient also, but Pearson is the most widely used. This is the most widely used because mostly we deal with numbers, data, okay, numbers. So this is used, and then other one makes sense in the special case, which I'll discuss later. Okay, so whatever I said, +1, this is for R also, the same thing will be valid. Okay, and it can be, we can get anything between -1 to 1. Say for example, a correlation value of 0.9. It is not perfect one, but it shows that there is strong correlation between x and y. So x and y, if I get correlation r is equal to 0.9, and there's a strong correlation in the positive direction. They are not exactly the perfect one, means if one is changing perfectly that will change, but it is very close to that. And similarly, if it is like minus 0.7 means negative. If one is changing, then other one is also changing, not exactly strongly but somewhat in the negative direction. It gives me, and also gives the magnitude that whether it's very tightly aligned and moving very strongly with the variable, or it is somewhat not so strong. Okay, it is less than the perfect change. We will draw some graphs sometime. I'll show you. Okay, in some other video I'll show you all the correlations. There's a very beautiful graph I have seen for different plots. Say if x and y are like strongly correlated, the graph would be something like this. X is equal to y, like this. The plots will be here, the points will be x and y. If x and y is in this, negative correlated means like this. So there was a beautiful plot. I'll show you sometime. Okay, I'll create on the video, but for now let's focus on the maths. When I go to the plots, I'll show you that. Okay, so that is there. So let's see if I can do the example quickly. Let's continue the example. So what is the formula? Okay, I missed for this. The formula is r is equal to covariance of x comma y, and for standardizing we divide it with their standard deviation of x and standard deviation of y. So this will be x and y, whatever units they are coming. Say for example, this is in height and age and height. Then this will be age comma age into centimeter. Then again this will be in standard deviation by age, and this will be centimeter, and that's how this will be cancelled out, and then this will be unitless, and that's how we can compare. I hope this is clear. Why this is unitless and why this is called standardized. And let's continue the example that we saw. So for example, let's solve the example that we have. So we had covariance of x comma y was equal to 2, and where x was equal to 1 comma 2 comma 3 and y was equal to 2 comma 4 comma 6. Okay, y is equal to 2x, strongly correlated. Let's compute quickly the correlation coefficient, Pearson correlation coefficient of this. So this will be equal to, so r will be equal to covariance of xy minus sigma x into sigma y. So covariance xy we have calculated 2. What will be the standard deviation of this? So distance from the mean. So this is our mean, 2 here, 4 here, square by, again n minus 1 correction factor will be there for sigma x. So this will be 1 minus 2 whole square plus 2 minus 2 whole square plus 3 minus 2 whole square into, this is my sigma x, again square root of 2 minus 4 whole square plus 4 minus 4 whole square plus 4 minus 6 whole square by n minus 1, that is equal to 3 minus 1, that is 2, that is equal to 3 data points we have, n is 3 here, 3 data points we have, and 1 2 3 1 2 3, right? So this is the correction factor which we used here also. Unbiased estimate, Bessel's correction, n minus 1. So same thing we'll use for the covariance and for the standard deviation also, because that is square root of variance, and then variance also has that correction factor of 1 by n minus 1 instead of n. So let's calculate this. This will be equal to 2 by, this is a square root of 1 plus 0 plus 1 by 2 into square root of 2 minus 4 is 4, 2 square plus 0 plus 4 by 2. So this is equal to 2 by 2 square root of 1, no problem, into 8 by 2 square root of 4. This is equal to 2. So this is 2 by 2. This is equal to 1. So my r is equal to 1. So this is a perfect correlation. And that's what we saw, that it is a perfect correlation. If x changes, y changes, it's a perfect correlation. Right? Now let's move to the next one, the next way. So this is used for ordinal data, okay, whenever categorical data. whenever we have categorical data, right? So that time these numbers don't make sense. I'll give you an example. Spearman's rank correlation coefficient. Also, there's one more important note. Okay, let me talk about that too. So there's a basic assumption, okay, that in this Pearson's correlation coefficient, that there's an important assumption that the underlying data is normally or Gaussian. Assumption is normally distributed data or Gaussian distribution. So data is Gaussian or normal. So this is a parametric. So because of that, this whatever that final this output comes, right, this formula comes, that the assumption is based that the data that we are handling, that is Gaussian or normal, and for that this formula holds. And for this Spearman, on that note, Spearman is a non-parametric. Okay, the Spearman's rank correlation coefficient is a non-parametric measure of correlation. This is a non-parametric. This term will come again and again, parametric and non-parametric throughout statistics. So non-parametric measure of correlation that uses, so the name has, that uses a rank instead of raw data. And what does this non-parametric mean? So this was parametric because it assumed that the underlying data is Gaussian. This is non-parametric means it doesn't assume anything about the underlying data distribution. Here it is assuming that then my data, whatever I'm talking, is it should be normally distributed. Normally it should be bell shaped. That's why this is a parametric test or parametric metric. Here this is non-parametric because it is not assuming anything about the underlying data. That's why this non-parametric is there. I'll talk about this again and again so that it becomes very clear in your head when it becomes parametric or non-parametric. It talks non-parametric means does not assume anything about underlying data. Simple. Always whenever I talk about this, that's what it means. And this, I said, this is for linear relationship, right? I have mentioned somewhere. Linear relationship. Even this is for measuring linear relationship. You saw here x is equal to 2y, y is equal to 2x. This is really linear. X and y related, and this is a power of x and y are 1, and this is the multiplication factor, whatever the coefficient is there. But the power of x and y is 1 here. So that's a linear relationship. That's what Pearson assumes. But this Spearman's rank coefficient, the first of all, that is non-parametric. That is first point. Second thing, it uses ranks of the data instead of the data itself. It uses a rank of the data. First, it orders the data in rank 1, 2, 3, 4. Okay, and then it compares. And the third thing is it is monotonic. Okay, captures monotonic. Monotonic means increasing or decreasing. Captures monotonic relation. Okay, increasing or decreasing, whatever direction, or decreasing. Monotonic word is important. Means if x increases, y also increases. It may or may not be linear. Okay, not necessarily linear. Not necessarily linear. Linear means here, as you saw here, right? Y is equal to 2x is linear, but y is equal to 2x square, this is not linear. This is quadratic. I hope you understand. Y is equal to e to the power x. This is exponential, not linear. These two are not linear. I hope that is clear. So this is power 1, here 2 power 2, and this is exponential. So this is totally different curve itself. This is just grows like this. Y equal to 2x square will be something like this. But one side it is decreasing, one side it is increasing. But if I take just the positive side, then it's increasing only. That side it is monotonic. Monotonic means if x is, so both should change in the same direction. Increase means both should change. If y, here it is like half side of this exponential, means if y is changing, x is changing positive side, then y also changing positive side only. It should not go down. So that's what monotonic relation capture means. I hope that is clear. And it just quantifies, okay? It quantifies in terms of ranks, okay? How well ranks of one variable predict the ranks of other variable. Instead of the exact raw data, how quantifies how well ranks of one variable predicts the ranks of other variable. Okay, and the range again is same, and it is denoted by a symbol rho. I'll just write it. This is rho symbol. In electrical engineering, you would have studied resistivity. That is the same resistance. The resistivity was rho. So this symbol, Greek symbols keep coming. So this is that rho. Okay. So range is again range of rho is -1 is less than equal to rho is less than equal to 1. Same range for the coefficient. Anything standardizes -1 to 1. So again, this is what is monotonic is. So it can be anything that is increasing, and linear is just one type of monotonic. It can be quadratic, it can be exponential. Log x is also monotonic. So these are also when x increases, y increases. So these all are monotonic functions. So linearity is just one kind of monotonic function. I hope that is clear. Now let's move. Let's see an example. So generally there's a we calculate the ranks of the data for each of the variables separately, and then we calculate the Pearson correlation coefficient on the ranks. We don't use the data, but we do Pearson correlation coefficient on the ranks that we have computed. Okay, not the original data. That's what it means. But there's another specialized formula also, that this is equal to this rho is equal to 1 minus. I'll not go into the derivation of this. 6 times di square. I'll tell you what does it mean. And then this is n by n square minus 1. This is one formula is there. So just this is used for wherever the data is of some category or ordinal, some order is there in the data. It is not just numeric like 1, 2, 3. Then we use this Spearman's rank, where we have ranks and ordering. Let me give an example that will make it clear. For example, I have data. So there is a student. There are 5 students, for example, and they are ranked by 2 teachers. And now I have to find out what is the correlation between the ranking given by the 2 teachers. Whether they are highly correlated or one teacher has given just the opposite rank of what the other teacher has given. So we want to find the coherence or some correlation between the ranking of the 2 teachers given for the 5 students, so that it makes sense, so that the comparison becomes more objective. We have more metrics to prove that okay, these students are really what the teachers are doing, or it is not like all over the place. So let's see with an example. For example, the students, okay, and then there is a teacher A rank, and then this is teacher B rank. And then there's a difference. This di is the difference in the ranks, and then it does di square. Okay, we want di square, it's summation of all. So students, say for example, there this is A, B, or let me do student 1, student 2, student 3, student 4, student 5. 5 students are there, and the first teacher ranked them as normally 1, 2, 3, 4, 5. Teacher A is ranked. This is the order they ranked them. And now the second teacher has ranked them like this is 2, and this is 1, 3 is 3, and 5 and 4 they have changed. This is 5 and this is 4. This is what the other teacher ranked. So this is swapped and this is swapped. Okay, this is the rank. So what is the difference here? So rank difference. This is di is the rank difference with the rank. The 2 minus 1. Okay, what minus 2? So we'll go this 1 minus 2 is minus 1 either way. And di square is 1. 2 minus 1 is 1. 1 square. 3 minus 3 is 0. This is 0. 4 minus 5 is minus 1. 1 minus 1 square is 1. And 5 minus 4 is 1. 1 square is 1. Okay. So summation over I di square is equal to these all sums. 1, 2, 3, 4. equal to 4. So what will be my rho equal to? Is equal to 1 minus 6 times sigma di square by n into n square minus 1. Here n is 5. 5 students are there. N is equal to 5. You can see 5 students. So rho is equal to 1 minus 6 into di square, we have calculated 4. N is 5 into 5 square is 25 minus 1 is equal to 1 minus 6 into 4 by 5 into 24. 4 and 6 is 24 and this 24 goes. So 1 minus 1 by 5, this is equal to 0.8. So my rho is 0.8. So this shows that there is a strong correlation between the ranking of the 2 teachers, the 5 students. But using Pearson, we cannot compute because these are not raw numbers. Because here the Pearson won't make sense because we don't have raw numbers, but this is directly a rank. This is ordering. And this is where Spearman's rank correlation coefficient shines. This is the utility for which it is designed. I hope Spearman's utility is clear. Okay, now let's move on. And similarly, if we have, if we talk about monotonic relation, right? So I'll give you a quick example, do the maths, and I'll give you. So I'll give you, for example, 2. I have x is equal to 1, 2, 3, and earlier y was 2, 4, 6, right? And now instead of that, for example, if there is a cubic relationship, so y is equal to x cube. Earlier it was 2. So 1 is 1, 2 is 8, and 3 is 27 now. So as x is increasing, y is increasing. There is a monotonic relationship, and they're increasing. But this is not linear. This is monotonic, but not linear. See the power here. Power is not 1. So here you see the ranks are same. One is the order of these numbers and the rank of these numbers is same. So the Spearman rho will come as perfect plus 1. But if you compare the covariance and then you do sigma x and sigma y, right, the r value if you compare. So r will come out, okay, that rxy, that is the Pearson. Rxy is a Spearman's rank. Pearson's coefficient will come out to be something close to, do the calculation. I have done calculation earlier, I'll tell you. This will not come perfect one, but it will come something around 0.9662. Just put the numbers, you will get it. Okay, but this is perfect one that is telling, and that is giving you, yes, it is capturing the monotonic relationship. But if you see, this can capture a linear relationship and it is not able to capture this cubic relationship, and that's why it is not giving perfect one. But if you see from the ranks perspective, both are strongly positively correlated. I hope this is clear, the application of both. Now let's move to the utility. Why are we in machine learning? Why are we reading applications of correlation? So in feature selection, so mostly we use correlation in machine learning for feature selection. We have multiple features in machine learning. We'll have multiple features to predict a target variable. Say for example, if I have multiple features for predicting an old car's price, like for example, how many years old it is, which brand it is, which make it is, okay, whether it has all the features or not, ABS is there, and etc, all the features. So all these are different features on the odometer reading. So basis of all these features, you predict the price of the car, and then this is what a simple machine learning you do. So the price of the car is the target, and these are the features on the basis of which you predict the old car's price. But this correlation will come into play to see whether these features, out of these features, are some of the features highly correlated, and if they're correlated means they're not bringing any new information. So get rid of one, whichever you want to keep. So whichever are correlated, if there are two features which are highly correlated, like +1 or close to that, 0.9 and above, so you want to get rid of one feature because it will give to another problems. When we discuss machine learning in detail, that time we will discuss this. It will lead to a problem called multicollinearity, and that is because we have highly correlated features. So we want to get rid of these features. Anyway, it is not bringing any new information, so we can get rid of it. Okay, that is one utility. Other way, on the machine learning, on the feature engineering itself, on the feature selection itself, that if a feature is highly correlated with the target variable, means if some feature, say for example, how many years the car is old, and that will be highly correlated with the price of the car. So if that is the case, then that will show you that you have to keep this feature. You have to keep this feature. This is highly correlated. The years of how old the car is and the price it is buying. So you should keep this feature. And similarly, if there is some feature in the that you have collected, and that is not adding any value to the car price. For example, what brand of tires does the car have? It doesn't matter. It is like kind of, it doesn't impact the price of the car. So that will be kind of zero correlation. So you can get rid of that variable unnecessarily that will be there in the calculation without adding any value. So I hope you get the utility of correlation in machine learning model. So with that, correlation is done.